Hi class, today we're going to start section 4.3, which is on logarithmic functions. And this is a part 1 video. It's a little bit of a long section, so I wanted to make sure we had enough. It didn't go too long. Okay, so every exponential a to the x for a greater than 0 is a one-to-one function. By the horizontal line test. And what one-to-one means is that for every input, you have a unique output. So there's no repeat outputs, or basically if you have like f of x equaling 6, there's only one x that will give that number. Okay, so by the horizontal line test, and therefore, has an inverse image. Or a function, an inverse function. So the inverse of an exponential function is called the logarithmic function with base a. And is denoted log little a, or sub a. All right, so now we're going to really just define it in all of its detail. So let a be a positive real number with a not equal to 1. The logarithmic function with base a denoted log sub a is defined by this following thing. So log a of x equals y is equivalent to a of y equals x. So this is the main point of this definition. So what this means is log a of x is the exponent to which the base a must be raised to give x. Okay, so I know that this is kind of funky and kind of a weird definition and a weird function to work with, but this kind of means that if you have a log base a of x, you'll get out x, because the output of this function, log sub a of x, the output is what a must be risen to give x. So we'll use this definition And I'm going to do some examples later with real numbers, so it's a little clearer. Don't worry. So we'll use this definition. To switch between the logarithmic form and the exponential form. And I will probably abbreviate them several times as just log form and exp form or exponential form, just for ease. So in log form, we would have log of sub a of x equaling y. So this is our base, and this is our exponent. For when we have a, y equaling x. So again, this is our base, and this is our exponent. Okay. So now we're going to do an example that is switching between the log and exponential form. Okay, so we're going to have the log form and the exponential. So first, let's look at log base 10 of 100,000. This equals 5. And this is because 10 raised to the 5th equals 100,000. And something that's helpful with base 10 is when you raise 10 to a power, that's how many zeros you will have after the 1. Which let us know here, there's 5 zeros, so our output was going to be 5. So that's just a helpful tip for when we're working with log base 10. But then we can also look at log base 2 of 8. This equals 3. And so over here, that means that 2 raised to the 3rd power, this equals 8. So you can see that these kind of match up. So it's 2. What do we need to raise 2 to get 8? And the answer is 3. And then checking over here, 2 cubed equals 8. Similarly, if we have log 2 of 1/8, that will give us -3, because 2 to the -3rd power, that gives us 1/8. And remember, when we work with 2 to a negative power, that's similar to having 1/2 raised to the 3rd power, which we do know equals 1/8. So, and then for one last example, just using kind of a more generic number, if we have log 5 of a equaling b, that means that 5 raised to the b power equals a. Okay, and now we're going to do some examples of just computing the outputs of when you get a logarithmic function. So if we start with bullet point, not a minus sign. So if we start with log base 10 of 1,000, what does this equal? Well, so we're going to look at what power do we need to raise 10 to get out 1,000? Well, from before, we knew that since there's 3 zeros here, that means we're going to have a 3 raised here. So log base 10 of 1,000 equals 3. Okay, so then looking at our next example, if we look at log base 2 of 32, what does this equal? Well, 2 raised to what power will equal 32? And if you don't know the powers of 2 just off the cuff, that's fine. I usually don't. So I like to make a little table, kind of 1, 2, 3, 4, 5, 6. And then on the other side, it'll be like 2 raised to the first power, that's 2. Then you double it, and you get 4. If you have 4 times 2, that's 8. 8 times 2, 16. 16 times 2, 32. So that means here, this is what we wanted. So that means that 2 to the 5th equals 32. So log 2 of 32 equals 5. And then if you wanted to keep going with the table, there would have been a 64 here, but we found the one we needed, so we didn't need to go further. And then now looking at one last example for this part, if we look at log based 16 of 4, well, we need to think 16 raised to what power equals 4? Well, we know that the square root of 16 equals 4. So that means that 16 to the 1/2 will equal 4, because the square root is equivalent to raising a number to the half power. So then that means log of 16 of 4 equals 1/2. Okay, so now we're going to move on and we're going to look at something called the properties of logarithms. So first, log base a of 1, this equals 0. And that is because a of 0 equals 1. And then log base a of a, this equals 1. And that's because a to the first power equals a. And then 3, log base a of a to the x, this just equals x. And this is because a raised to the x power equals x. So to get a to the x as our output, we need to have x as our input. And it's also because they're inverse functions. So if you apply them to each other, they cancel each other out. So we'll see that here. A raised to the log based a of x power, this also equals x. And this is because they are inverse functions. So recall from 116, f inverse of f of x, this just gives us back x. Okay. So now we're going to look at how to graph a logarithmic function. Also, these properties up here, these are pretty important that you know. You're going to be using them a lot in this section. Okay, so moving on to graphing logarithmic functions. So since we're working with the inverse of an exponential function, the domain and the range swap. So for example, if we have f of x equals a to the x, this has domain all of r, or all of the real numbers, and range all of the positive numbers. So then if we look at the inverse image, which is log base a of x, we're going to switch domain and range. So now the domain is 0 to positive infinity. So that means the numbers we can input into our function are lying here, and then our range is all of the real numbers. And for when we graph something like this, you should remember that when you graph something, it will be an inverse function. The graph is reflected about the y equals x line. So if you remember, a of x looks something like this, where this is 1. So that means that log a of x is going to look something like this, where this is 1. This is log a of x. So it has just been reflected across this line here. All right, and where a to the x had a horizontal asymptote at 0, log a of x has a vertical asymptote at 0. You see how this line here, it never quite touches 0? So that's how we know we have a vertical asymptote. Okay, and it also works in the opposite effect as when a to the x gets bigger when you have bigger a's in there. For log a of x, the graphs get slower for the larger a's that we have as base. So that's another example. So we're going to start with, this is log 2 of x, and then this will be log 5 of x, and then down here, this will be log 10 of x. And they're all supposed to be going through this point right here, which is 1. So log 10 of x will grow slower than log 2 of x. Okay. So now we're going to look how to transform the graphs of log. So first, we're going to look at reflecting. And our first example of that will be looking at f of x equals, and we're going to use for our base just log 2 of x, similar to how in our other video we used 2 to the x, just to have like a sense, but it could work for any base. We just are going to use 2 because it's a nice one, pretty easy to work with. So if we're going to look at negative log of 2x, and this one externally affects the graph. what I mean by externally is this negative sign is outside of the function. This is the external reflecting part. And what that means is if we were to look at our graphs side by side, yes, so if we were to look at first log of A, and then negative log of A would look something like this. Or log of 2, sorry. Negative log of 2x. So here it reflects across the x-axis. Which we're pretty used to. It's very common that when you have a negative, like -1 times a function, that just rotates it across the x-axis. And here our domain, for our new function, we're just mostly looking at this one here, but it actually happens to be the same as log of 2x. Our domain is all the positive numbers, because we can input anything like excluding 0, because we have an asymptote, anything from 0 all the way to negative or positive infinity. And then our range is all of R, or all of the real numbers. I might just be saying all of R, and it's just because when you write the real numbers, you just draw this fancy looking R. So it's just my own wanting to shorten it. Okay, and then the next example we're going to look at is, sorry, I lost my spot. It is internally. It's just internal reflection. So we're going to look at f of x equaling log A of negative x. So this time we've scaled this inside number by a negative. So that means we look at our graph. Here is our original. Oh, oops, I wrote an A. I'm just going to make that a 2 again, just so it's a little more concrete. And then this over here, this is log 2 of negative x. So here we've rotated around the y-axis. All right, and now this is where our domain changes. So you can see where all of our inputs here on the x, they are negative infinity to 0. But our range is still all of the real numbers. Since we only have defined the original log as being able to put in positive numbers, we have to put in a negative number to make this part negative, because it'll be negative of like -6. That will become +6. I'm just going to leave that kind of as an example there. Okay, and then our next example is shifting graphs. So first we're going to look at external addition. And these should also seem very familiar to all the other ways we have looked at transforming graphs. So let's look at f of x equaling 2 plus log 2 of x. So let's start with our original graph here. This is our log 2 of x. And so since we are adding 2, that means we're going to shift everything up by 2. And I like to tend to look at the point here. Shift it 1, shift it 2. So this is kind of our new x-axis. It's all been shifted slightly. So that means our graph will look something more like this. Okay, so this is 2 plus log 2 of x. So all of these points have just been shifted up by 2. All right, and our domain is still 0 to positive infinity, and our range is still all of the real numbers. And now we are going to look at adding internally. So we're going to look at f of x equals log base 2 of x plus 3. So remember, when we add something to the inside, that means we're shifting it to the left. If this was subtracting 3, then it would shift the graph to the right. So here we go. Here is our original function. And then now we've shifted 1, 2, so 1, 2. Okay, so we've shifted our horizontal asymptote over here. So our new graph will look like this. It keeps going like that. And this is log 2 of x plus 3. So, and this is a negative 2 here. This is a positive 1, always. So now this is when our domain changes. So since we've shifted everything to the left by 3, that means our interval has also shifted. Now our inputs can be negative 3 to infinity, not including negative 3 because we have that vertical asymptote there. But our range stays the same. It's still all of the real numbers. And we have our vertical asymptote at x equals negative 3. All right, so that's it for just this part 1 video. I'm going to upload a part 2 video soon. So thank you guys for listening.